Hello. Welcome back. So, today is the last in the series of recordings that I'm making for the fact that I'll be out on March 5th. That's today. Um, so let's start in where we left off. I know that I said last night when I was recording that I wasn't going to go through the proof that this is actually a subgroup, but let's go through and do it. Um, so we have this theorem 3.3.4, which gives us a way to check if something is a subgroup. So I need to show that this H is non-empty. It's got two things in it. It's not empty. I need to show that it is closed under the operation of taking any element of H and multiplying it by the inverse of any other element of H. So that should be easy. And I guess in this case, by multiply, I mean add. And by inverse, I mean additive inverse. Because this is an additive group, not a multiplicative group. Well, let's do it. 1. H is non-empty since it contains 0 bar and 2 bar. Easy enough. Now we must check that for all variable names, H1, H2, H1, H2 in H, that H1, H2 inverse is in H. So let's just check one at a time. Oh, and additive group, not multiplicative. H1 minus H2. All right. Well, I guess we just have to check one at a time. So let's see. 0 bar minus 0 bar equals 0. 0 bar minus 2 bar is minus 2 bar. Oh, but this is z mod 4. That's the same as 2 bar. 2 bar minus 0 bar is equal to 2 bar. And 2 bar minus 2 bar is equal to 2 bar. Each of these is in this set that is called H. So by theorem 3.3.4, H is a subgroup of G. And because I don't trust myself to have written down the correct citation, I'm going to double check that 3.3.4 is the right thing to use. So scrolling up, there's 3.3.4. It says that if G is a group, yep, we have a bigger group, Z mod 4, and H is a subset of G. Yep, the thing I called H is a subset of that group. It is a subgroup if and only if it's non-empty. We check that. And it's closed under this operation, which, yeah, we just checked that. All right, neato. So one more example of just finding all the subgroups. Let's find all the subgroups of C2 cross C2. Recall, C2 is the abstract cyclic group of order 2. So its elements are a to the 0, which is 1, and a to the 1, which I'll just call 1. So the elements of C2 cross C2 are ordered pairs of 1 and a. So there's the lot of them. So let's first list all of the cyclic subgroups. Nope, the obvious one's first. So there are two subgroups that every group has. The whole group and the group that only contains the identity element. So I guess these two groups are just the identity. And C2 cross C2. So that corresponds to this and this. Nice. All right, so let's now list the cyclic subgroups. So I guess the cyclic group generated by the identity is just going to be the identity. That's easy to see. So now I need to check the cyclic subgroup generated by each of the other elements. And I think I'm going to opt to do this as scratch walk off to the side. So unfortunately, if I like rotate, the screen will auto rotate. So let's do some scratch walk. All right. Cyclic subgroup generated by, you know what? I think I'm only going to do one. I'm going to do the cyclic subgroup generated by AA. So let's just start listing elements. So I don't know. So I don't have to write so many things. I'm going to call that T. T to the 0. Anything to the 0 is the identity element. So that'll be 1, 1. T to the power 1 is T, so AA. T squared is AA times AA. And recall, in the Cartesian product of two groups, I just multiply pointwise. So that's A times A, also known as A squared, comma A squared. Ooh, this is C2, right? Cyclic group of order 2. Back to 1, 1. So T cubed, well, that'll be T squared times T. So that'll be 1, 1, because that's T squared times AA. Oh, yeah, we're back to AA. And now maybe you see the pattern. It's just going to keep on alternating between 1, 1, and AA. All right. The next thing is to list the cyclic subgroup generated by the other two non-trivial elements. And, oh, those shouldn't be zeros. Those should be ones. It's a multiplicative group, not an additive group. We don't call the identity in a multiplicative group 0. Cyclic subgroup generated by A1, it's got to contain the identity, and it has to contain that thing. Excuse me. And now you can repeat that same bit of scratch work to see that that is the cyclic subgroup. Cyclic subgroup generated by 1A, well, it's going to contain 1, 1, and it's going to contain 1A, and that's it. All right, so that gives us 3 subgroups. A1, 1A, parentheses, bracket, AA. And I guess this is suggestive that I am now claiming that those are all of them. So each of those are bigger groups than 1, 1. Neither one of them contains the other. So I'm not going to draw any lines between, say, that one and that one, because neither one is a subset of the other. Each of these is a subset of C2 cross C2. So there's the lattice diagram for C2 cross C2. Oh, and that's notationally maybe problematic. I should be consistent with notation. If I'm calling that one C2 cross C2, I should also call this one C2 cross C2. But as we said when we introduced the notation, I'll use that symbol O plus and the slash time symbol interchangeably. If we get to non-finitely generated groups, there's a difference when you take like an infinite Cartesian product. But we'll deal with that when we get to it. All right, so we found these 3 cyclic groups. Well, what's the only other way that we could form a group? Any other group would have to contain, well, if it only contains the trivial element, we've already listed it. It's that one. If it only contains the trivial element and one of these 3 things, then it's in that list. So any other group would have to contain at least 2 of them. I claim that that would mean that H is in fact all of C2 cross C2. And let's just check that. So let's go ahead and assume you pick two. I'll pick the two that I underlined in pink, but you pick whichever two you like and see if the same logic works out. Let's assume a comma 1 and 1 comma a are each in H. All right. So I need to show that H is all of C2 cross C2, and it already contains two of the elements. It contains this one and that one. If I want to show that this is all of H, I need it to contain a comma a and 1 comma 1. So let's see. Since a subgroup must contain the identity, one must be an H. So I contain three of the four elements. Ooh, let's see one more. Since H is closed under the multiplication operation that defines C2 cross C2, a comma 1 times 1 comma a is in H. And now let's just do that multiplication. Thus, a times 1 is a, 1 times a is in H. As H contains every element of C2 cross C2, H is equal to C2 cross C2. And you might be ready to complain. I've only shown one set containment. I've only shown that C2 cross C2 is a subset of H. But recall, by assumption, H is a subgroup of C2 cross C2. Subgroup implies subset. That's one part of the definition of a subgroup. So I already had the reverse containment. Let's make the conclusion. All right, so we've now listed all of the subgroups. Thus, a complete list of subgroups of C2 cross C2, or C2O plus C2 if you prefer, is the trivial group, the cyclic subgroup generated by A1, the cyclic subgroup generated by 1A, the cyclic subgroup generated by AA, and all of C2 cross C2. All right. And now I'll actually say these words. So it's often useful to integrate all of these subgroups sorted by size. So if you like, all of the subgroups that are on the same horizontal level will contain the same number of elements. And then I'll draw a line from one layer to another if the bigger thing is a superset of the smaller thing. So I've drawn this pink line because this is a subset of that. And I haven't drawn a line all the way from 1, 1 to C2 cross C2 because you kind of already know that this is a subset of that because you know that this is a subset of that, and subset is a transitive operation. Sorry, transitive relation. All right. So one more important example of a subgroup. So a lot of times you want to find subgroups that have special algebraic properties. And here's one that is an important algebraic property. It's going to measure the failure of a group to be abelian. And recall, abelian is the word that means the elements of G commute with each other. So what's a way of measuring this? Well, it's an object called the center of a group. It's not the only way to measure that, but it's one. If G is a group, then the center of G, denoted Z of G, you can attribute the reason for that Z to the Jarman, is defined to be the set of all elements of G which commute with all other elements of G. So an element is in the center if it commutes with every other element of G. That's maybe even worth writing in just plain English. G is in Z of G. If and only if G commutes with every element of G. All right, so now let's put it in like the formal language. So Z of G is the set of all G in G such that for all, well, it doesn't matter what variable I'm about to use. I'm going to use H though. For all H in G, G and H commute. And what does that mean? That just means GH equals HG. So it's the set of all elements of the group G, which satisfy that for all H in G, GH is equal to HG. I've called this the center of a group. I'm going to do two things before I call it for now. I'm going to check that the center is actually a subgroup. And then I'm going to compute the center for a particular very non-commutative group. So this non-commutative group is going to be the symmetric group. I will show that the symmetric group has center equal to only the identity, the smallest possible subgroup. All right, let's try to do it. Proof. Let G be a group, right? Start with the assumption. In order to get the center of G not equal to the empty set, we will show that 1 is in the center of G. Oh, and maybe I'll point something out. If you say ZG, so avoid using blackboard bold Z here if you're in that habit. That's used to refer to something else. That something is called the group ring, which we might get to later on in this class. You can look it up. You'll figure out the definition if you look it up. Let G be a group. In order to get ZG, the center of G, to not be the empty set, we need to show that something is in there. Let's show that 1 is in there. So what do we need to do? What do we need? So in order to show that 1 is in the center, I need 1 to commute with everything in G. So I need 1 times H is equal to H times 1 for all H. Oh, well, that's the definition of the identity. Since 1 is the identity, 1H is equal to 1 is equal to H times 1 for all H in G. As we see that for all H in G, 1 times H is equal to H times 1. 1 is central. All right, something in the center of a group is called central in the group. All right, inverses. So I need to show that if something is in the group, I need to show that its inverse is in the group. So again, let's go off to the side. So what do we get to know? R is the thing I'm assuming is in ZG. I get to know that RH is equal to HR for all H in G. What do we want? The same thing, but with an inverse, because I need our inverse to be in the center. Let's see, like, it's annoying that there's an inverse on that R. If they want the inverse there, I could use that R is central. Well, let's think about what inverse means. Um, R inverse H, well, it's the same thing as R inverse H inverse inverse. And like that might seem like an oddball thing to do, but like I want to get one of those inverses off of the R. And this inside inverse will do that. This is equal to the big inverse will stay. When you invert something, you swap the order and get an inverse on each term. H inverse and then R inverse inverse R. Ooh, but R is central. And now I can put this inverse back onto things. Oh, cool. That does it, right? So let's put this into action. All right. So what do we got? We want to show closure under inverses, so we get to let R be in ZG. I need to show that R inverse is in ZG. I will now consider any X in G. Over here, it's H's off to the side, but we can use X's. If you want to switch that to a H, do it. So let's do it. We have like a string of equations on the right. I'm just going to follow that. R inverse X is equal to R inverse X inverse inverse. And maybe I'll put the justification on the line below. I think I have enough space to make this walk. Since Y inverse is equal to Y for all Y in G, that is now equal to big inverse stayed put, and now the inverse got distributed to the individual terms and they swapped order. Equals X inverse R inverse. So this is since Y inverse equals Y for all Y in G. The next thing we used is that AB inverse is equal to B inverse A inverse for all A, B in G. The next thing used in this stack was the fact that this thing is central equals R X inverse since R is central. And you know what? I think that's the last thing I need to write. So let's put the word and in there. Because now I'm just going to undo those steps. That is now equal to X times R inverse. Cool. Now, new full sentence. As X R inverse equals R inverse X for all X in G, R inverse is central. It's in ZG. Closure under multiplication. So let's go through the motions for that. And I think this one I'm going to write less. I'll leave you to write the words that I'll leave out. All right. So I need to show that R times S times X is equal to the same thing, but with X on the other side. Cool. Well, I know that X commutes with S and R individually. So you know what? I'm going to appeal to associativity to leave off these parentheses so I don't have to repeatedly say it by associativity. All right, let's go through these motions. Well, S is central. So R, that's equal to R times X times S. R is central. That's equal to X times R times S. Oh, cool. So that's like it. Since S is central and R is central, we are justified in not including parentheses since G is a group. Right, so associativity says that you don't need to include the parentheses anyway. Nice. All right, cool. So let's put the conclusion. Thus, R times S is in ZG. So what have we shown? We've shown that the identity is central. We've shown that if you start with a central element, then its inverse is central. And now we've shown that it's closed under multiplication. So I just want to cite the correct theorem. We have now shown that this thing satisfies not these conditions. We've shown that it satisfies these conditions. So 3.3.3 is what I'll use. Excuse me. All right. One last one. Let's compute the center of the symmetric group. So here's the claim. For any n at least 2, the center of the symmetric group is just equal to the identity permutation. So how do you show that two sets are equal? Well, you need to have an argument that each one is a subset of the other. One of those is like obvious. The center of a group is a subgroup. We just checked that. Every subgroup contains the identity element. So that containment is automatic. All right, so carrying on from there, I need to consider any central element of the symmetric group. So let's suppose that sigma is a central element. I need to show that this thing is not the identity is the identity permutation. So how do you do that? Well, I don't think I'm actually going to make a proof by contradiction. So I don't think I actually need that line. We'll put it back at the end if we need it. I need to show that sigma is the identity permutation. Oh, no, okay. So let's suppose that sigma is not the identity permutation. I'm going to get a contradiction. All right, I take it back. I should read a little bit farther ahead. I wrote the damn proofs. Sorry, I certainly shouldn't swear on recording. All right, so if sigma is not the identity permutation, then it moves someone. So there's something in Xn which sigma sends to something else, Y. I now have two elements named in this in Xn. X is an element of Xn, big Xn. Sigma of X, which I've called Y, is an element of big Xn, and they're not the same. So there's two elements so far. I am assuming that n is at least 2, so Xn has at least 3 elements. So there's a thought element, I'll call it Z, different from X and Y. In order to come up with a thing that will fail to commute with sigma, let's take the thing that swaps Y and X. All I'm going to do now, I want to show sigma tau is not equal to tau sigma. How do you show that permutations aren't the same? You show that there's some input that they send to different places. So let's go ahead and do that. So tau of X. Well, let's see, tau is just like the transposition of Y and X. It doesn't do anything to X. Sigma of X, I know what it is Y. In the opposite order, Tau of sigma of x. Well, sigma of x is y, so this is tau of y. Ooh, but tau of y, tau is the thing that swaps y and z. Ooh. So maybe I'll put like a sentence here. Thus, sigma of tau of x is not equal to tau of sigma of x. And so sigma tau and tau sigma are different permutations. As sigma does not commute with at least, you know what, let's use language that sounds less negative. Fails to commute with at least one element of the symmetric group, sigma is not central. So what have we shown? We've shown that every non-identity permutation, so every permutation that's not the identity, is not central. So every non-identity permutation is not central. And so the identity permutation, epsilon, is the only element of ZG, which is exactly what we needed. We claimed that only the identity permutation was central. We now have that. All right, so I'm going to point out one thing. There was an oopsie as I was posting the homework, and that whole thing wasn't actually finished listing. So here's the optional homework. You can complete this, or if you want, as like a challenging homework problem, or you can ignore it. So here is the claim. Here's what this is going to introduce you to. In addition to the subgroup generated by just one element, the cyclic subgroup, you can talk about subgroup generated by any subset. It's just anything you can get by a product of a bunch of elements of X, raised to any sort of powers. It is a subgroup. You can check that. This isn't going to have you do that. What I'm going to do is have you determine what the subgroup of S4 is generated by those two permutations. All right, cool. I've even started listing some of them for you already. What I'm going to have you do at the end is determine with proof what the subgroup generated by these is. Nice. All right. Keep in mind that there's like challenge problems and stuff associated. Some of you have been really good about being proactive about doing them already, but the rest of you keep them in mind. I'll see you on Friday. We'll talk some about this because this went very fast. And otherwise start in on a more in-depth study of cyclic subgroups of a group. All right. I hope you all have a good day. Maybe I'll see you during my office hours.